Okay.
Okay, let's start. So it's a pleasure to introduce Omar Antolín from UNAM in Mexico City. I will be talking about classifying spaces for commutativity.
All right, thank you. Thank you for inviting me to give this talk. I think many of you have heard me talk about this topic in this very room. So as to not bore you too much, I tried to focus in this talk on older stuff that you probably haven't heard me talk about before. So let me start by telling you what spaces I'm going to be talking about. And the slides are in Spanish. Most people can read Spanish in this room. Not everybody can, but so I often see here in Mexico people giving talks in Spanish with slides in English, and I've never seen the opposite happen. So I'm going to try to redress the imbalance a little bit. All right, so throughout the talk, G is going to be a Lie group. Sometimes I'll say a few things about finite groups. I guess finite groups.
Topological groups.
All the definitions make sense for topological groups as well, and but most of the interesting theorems have been proven only for Lie groups. The definitions make perfect sense. All right, so these classifying spaces for commutativity in groups are built out of the n tuples of pairwise commuting elements in G. So you can think of that as the space of homomorphisms from Z to the n into G. And well, that's a space. You can topologize that as a subset of G to the n. And you can put all of those together to make the classifying space for commutativity of G. But let me start by showing you what these spaces of commuting tuples look like. They can be a little bit more complicated than you might think. So let's do an example with SU2. That's the group of unit quaternions. I'll write a quaternion as A plus U, where A is the real part and U is the imaginary part. That's a vector in R3. In those terms, the only thing you need to know to multiply quaternions is what the product of two imaginary ones is. And there's a simple formula for that. Its real part is minus the dot product. Its imaginary part is the cross product. Okay, so with that formula, it's easy to check that two quaternions commute if and only if their imaginary parts are parallel. Okay, so the space of commuting pairs in SU2 is the set of pairs of quaternions where the imaginary parts are parallel to each other. All right, so let's build that space. Let's think of unit imaginary quaternions. That's a copy of S2. And then for the real parts, we need one more number. So look at the space S2 cross S1 cross S1. We'll identify two tuples there if we'll identify VAB with minus V A conjugate B conjugate. And we can use these to build two quaternions that have parallel imaginary parts, right? If you have this vector V, unit vector in S3, think of it as a purely imaginary quaternion, and you have two complex numbers with norm 1, you can form those two unit quaternions, right? And so this map from this quotient space to the space of commuting pairs is surjective, right? Because of what we said on the previous slide. And it's surjective, but it's not injective. It only fails to be injective in a few regions. If the unit complex numbers you picked are plus or minus 1, then since A2 and B2 are 0, what vector you picked for V doesn't matter at all, right? So it squashes down those copies of, well, those quotients of S2, right? So if you fix the choice of signs here and let V vary, this is a copy of RP2, right, in the quotient, that gets collapsed down to a single point. So the space of commuting pairs of quaternions is, you start with this quotient space, S2 cross S1, identify the triples as I said above, and then find 4 copies of RP2 inside, and each of them you squash down to a point.
So 4 blow downs.
Yes.
And they intersect these copies of RP2?
No, those are completely disjoint. They come from the different combinations of signs there. Yeah, right. So I don't know. That space may or may not be more complicated than you thought it would be. And you can more generally talk about spaces of homomorphisms from from discrete groups into topological groups. And if the discrete group is finitely generated, there's a clearly a good topology to put on this space. You just look at, you can identify a homomorphism with the images of a set of generators, and then it's a subspace of G to the n. And these spaces of homomorphisms, as I've already said, are maybe a little bit more subtle than you might expect. So my intuition is trained from algebraic topology, and there I'm used to the fact that if you have a homomorphism of topological groups that is additionally a homotopy equivalence, then those two groups are pretty much the same for many purposes. In particular, their classifying spaces are homotopy equivalent, which means that, you know, for example, the theory of principal G bundles and principal H bundles is the same. And you might expect some of this homotopy invariance to extend to these spaces of homomorphisms, which have a simple definition, but it doesn't. It doesn't. If G and H are homotopy equivalent via homomorphism, there's not much you can say about the spaces of homomorphisms from some finitely generated discrete group gamma. They may even have different numbers of connected components, right? And pi 0 is like the first invariant I always look at, and so not even that has to agree. And you might think, okay, so maybe not arbitrary homomorphisms that are homotopy equivalences, but not even the good ones. Like if H is a Lie group, then it has a maximal compact subgroup, and the inclusion is a particularly nice example of a homomorphism that's also a homotopy equivalence. And you might hope, well, at least for those, I do get homotopy invariance. And no, you don't. Not even the number of connected components stays the same. So they are a little bit more subtle than you might expect. This slide is intended for a different audience. I'm sure everybody knows what the maximal compact subgroup of a Lie group is. But let me just remind you of the basic examples. If you have a GLNR, its maximal compact subgroup is the orthogonal group. For GLNC, it's UN. And so here's a nice example of the number of connected components not being the same. This is from a paper of Alejandro Adem and Fred Cohen's. In their example, gamma is the fundamental group of a surface of genus at least 2, right? And you take for the Lie group SL2R. Its maximal compact subgroup is SO2, and it's a funny coincidence that the maximal compact subgroup is abelian. And that causes all sorts of trouble. So it's known that there are faithful representations of gamma in SL2R. And so look at this diagram. If you take any homomorphism from gamma into SO2, since SO2 is abelian, that actually factors through the abelianization of gamma, which is the first homology of the surface. And you have this commuting square, and the fact that this on the top is a homeomorphism tells you that alpha can only hit connected components that come from here. So it can only hit connected components where the homomorphism factors through the abelianization of gamma. And in particular, it will not hit the component of that faithful representation. So you don't even get a bijection on connected components. All right. Okay. So, all right. But there, gamma was the fundamental group of a surface. What if gamma is an easier to understand group than that? Well, let's look at the situation for z to the n, which gives us commuting n tuples. There's a theorem of Alexandre Petit and Juan Suoto that says that there are good cases in which you do get a homotopy equivalence between commuting n tuples in G and commuting n tuples in the maximal compact subgroup. This happens when either G is the space of complex points of a reductive algebraic group, or it's the space of real points of a real algebraic reductive group, right? And so that includes many of the familiar examples of the classical groups, GLN, SLN, SUN, SON. So in all of those cases, for commuting n tuples, you do get a homotopy equivalence. And if you're a topologist like me, you can forget about the linear group and study the orthogonal group, which is compact. Compact is often nicer. This theorem is also true. So you can replace z to the n with finitely generated free nilpotent groups. This means, so these are just the quotients of free groups in the descending central series. And it's even true for just finitely presented nilpotent groups. That extension is due to Maxime Bergeron. So all of these, so these results are for reductive algebraic groups. And it's definitely not true if the group is not algebraic. Here's a simple example. This is one of the several very similar groups called the Heisenberg group. So that group is not algebraic. And yeah, so I think there are a bunch of algebraic geometers here who are well aware of this. But for non-algebraic geometers, I always point out that multiplying matrices here involves using the canonical map from R to R mod Z, and that's the exponential, which is transcendental. That's why this is not algebraic. So it's very easy to just do the calculation and see that two matrices of that form commute if and only if AY minus BX is an integer. And so that means that the space of commuting n-tuples has infinitely many components, right? Because that integer definitely pairs that have different values for that integer will be in different components. Okay? And the maximal compact subgroup here is that R mod Z in the corner. So the space of commuting n-tuples in the maximal compact subgroup is connected. It's just that maximal compact subgroup is S1, and the space of commuting n-tuples is just the n-dimensional torus. Okay, so you definitely need some hypothesis. The one we know works is algebraic reductive or real algebraic reductive. Okay, so now these spaces of commuting n-tuples can be assembled to form the classifying spaces for commutativity in the title. Those are, so I don't actually know how that this is true, but I imagine that the reason Alejandro, Fred, and Enrique Torres-Giese started studying them is just that they noticed that you can assemble all these spaces of commuting n-tuples into a simplicial space. And I once heard Fred Cohen say that whenever you have a simplicial space, you just have to take the geometric realization and find out what it is. And so once you notice that something assembles to form a simplicial space, then you have no choice in the matter. You have to take the realization.
This was also observed by Morava, wasn't it?
Yes, and I don't remember the timeline now. Yeah, I don't know if they were aware of that. Yeah, yes, you showed me that paper. I think they don't cite it, so they may not have been aware of it. Right, so if you look for all n at the space of commuting n-tuples in G, those spaces assemble to form a simplicial space, and it's a subsimplicial space of the usual simplicial model for BG. Okay? And so if you're not familiar with what simplicial spaces are in geometric realization, all that means concretely is that this classifying space for commutativity is defined as a certain quotient of the disjoint union of these products. You take the space of commuting n-tuples. For each commuting n-tuple, you take a copy of the simplex, and then those are all glued together by some rules that I'm not describing. But it's a simple and explicit procedure to make a space out of these things. All right. And so, as I said, it's a subsimplicial space of one of the usual ways of building the classifying space of the group. So you get a canonical map from the classifying space for commutativity to BG.
This bundle theory is not homotopy invariant in G.
No, it's not. Yes, that's absolutely right. So that brings me to the next point. Why is it called a classifying space for commutativity? Again, I should just check with Alejandro instead of guessing at the history. But my guess is that initially it was called that because it's very similar to BG, and then only later did they figure out what it classifies. Right? Once you're in the situation of calling something a classifying space, you're sort of obligated to find out a thing that it classifies. So this was invented later by a process of reverse engineering, is my guess. Okay, so BG classifies principal G bundles, and so you need to come up with some sort of commutative principal G bundle that's classified by B comm G. And so part of the story is pretty nice. You can of course describe principal G bundles by means of cocycles, sets of transition functions. So if you have a set of transition functions describing a principal G bundle, you can ask whether or not that cocycle is commutative, meaning that whenever you have a point that's in two double intersections of opens in the trivializing cover, that the values of the transition functions at that point commute, right? So you can just ask, transition functions always commute pointwise throughout the intersection of their domains. And if that's the case, you can call the cocycle a transitionally commutative cocycle. All right, so Alejandro Adem and Jose Manuel Gomez showed that if you have a principal G bundle with a trivializing open cover that has that property, then you can build a factorization of the classifying map that goes from X to BG through BCOM-G. Okay? So we'll say that this data, a cover for which the transition functions pairwise commute, specifies a transitionally commutative principal G bundle, which should have a shorter name. And okay, but then I still need to tell you when two such pieces of data specify the same transitionally commutative principal G bundle, and there we sort of give up and say, well, they specify the same one if the classifying maps are homotopic. So the definition is partially in the language that you would see in differential geometry and partially in homotopy theory, right? We can specify them with geometric data, but for the equivalence, the best definition we have is that the classifying maps are homotopic.
Probably there is one, lots of diagrams and things.
That might be the case. So far, yeah, so far a nice definition of the equivalence that doesn't go through homotopy has not been found. And so that would be nice. That would be very useful in getting more geometers interested in these transitionally commutative principal G bundles. All right, so let me make issue some warnings about this concept. So as I said, to specify a transitionally commutative G bundle, it would be enough to have a principal G bundle and choose a trivializing open cover for which the transition functions commute, right? The choice of the cover is the data that specifies this factorization through BCOM-G. And so for the same principal bundle, there might be many different open covers that give non-homotopic maps to BCOM-G. So a single principal G bundle can have 0, 1, or any number of transitionally commutative structures.
Liftings to BCOM.
Yes, that's right. So if you have a principal G bundle, it's classified by a map to BG, and then transitionally commutative structures on that bundle are just lifts through BCOM-G. And there can be none, or one, or many. And there definitely are some principal G bundles that have no transitionally commutative structure. Obviously, the universal one shouldn't have one. Otherwise, there's not much difference between transitionally commutative bundles and just regular bundles. Okay. So this canonical map we had from BCOM-G to BG, that classifies a principal G bundle. And so call the total space ECOM-G, right? That's just the pullback, exactly. And so this, since it is the pullback, it's not contractible, right? That's a difference with the classical theory where EG is contractible. Since this is the pullback of EG along that map, and this map is most likely not a homotopy equivalence, then the pullback is not going to be contractible in general. If G is abelian, then our definition of BCOM-G is exactly the same as the definition of BG, and for abelian G, ECOM-G is contractible. And you might wonder about the converse. Is it true that ECOM-G is only contractible when G is abelian? And so there is some progress on that question. So it's been proven for several classes of groups that ECOM-G contractible implies that G is abelian. This is true for discrete groups. This is true for compact Lie groups. And some of you heard me talk about this in this room a few months ago, where I said we had proved it for compact connected Lie groups and conjectured it was true for all compact Lie groups. It's been proven that it's true for all compact Lie groups. It's also just not true in general. It's for SL2R, which has this uncomfortably abelian maximal compact subgroup. They are the ECOM-G, ECOM SL2R, turns out to be contractible, and SL2R is not abelian, so it's just not generally true, but it's true for compact Lie groups. Okay. All right, so there's a small variant of these spaces that's interesting because the spaces of commuting n tuples are often not connected, even if G is connected. Even for G equal to SO3, the spaces can be disconnected. So there's a variant where you only take the connected component of the identity. How am I?
No, you're okay.
Okay, yeah. And,
Almost.
Okay, good. Let me just denote the connected component of the constant homomorphism with value 1 by a subindex 1. Those connected components form a subsimplicial space of the one we use to define B, G. So there's a corresponding B, G1 that only takes into account that connected component. And there is an E, G1, which again is the pullback of the bundle. It's the total space of the principal G bundle defined by the canonical map to BG. Right? So for many groups, there's no difference. For lots of the classical groups, and here I'm going to focus on compact Lie groups G under the pretext that if the compact Lie group is the maximal compact subgroup of a reductive algebraic group, I know that I'm also studying the whole reductive group. Okay, so most of the work on these spaces has been in the case that G is compact. So for some of the classical compact Lie groups like SUN, UN, or the symplectic group, those have the property that every abelian subgroup is contained in a connected abelian subgroup in some torus. So in that case, the space of commuting n tuples is just connected, and there's no difference between these two variants of the classifying space for commutativity. All right. So let me tell you in what sort of basic structural calculations had been done in the original paper on these spaces. Well, not the paper where they were first defined, but the paper where they were first systematically studied by Alejandro Adem and Jose Manuel Gomez. All of their calculations are for compact connected Lie groups. And let me use standard notation from Lie theory. T is the maximal torus, N is the normalizer, and W is the Weil group. And so let me remind you that the classical way of presenting results about the cohomology of the group or the classifying space is in terms of these other subgroups, of these other groups. So for example, Borel's calculation is that the cohomology with rational coefficients of BG is the Weil group invariance of the cohomology of the maximal torus, of the classifying space of the maximal torus. In the same vein, Alejandro and Jose Manuel showed that for this variant where you take only the connected component of the trivial homomorphism, the rational cohomology is given by this expression. You take the cohomology of the classifying space of the maximal torus, the cohomology of G mod T, and then the Weil group acts diagonally on this tensor product. The Weil group invariance gives you the cohomology of BG, of B, G sub 1, the component of 1.
So G mod T is not a group?
No, that's right. G mod T is not a group. But it's a very interesting manifold that you associate to a Lie group, and it appears in a lot of these formulas. And for E, G, for the total space of the corresponding principal G bundle, you have a very similar description, except that both factors are the cohomology of G mod T. And in that paper, as another structural result, they also proved that E, G sub 1 has the homotopy type of a CW complex with finitely many cells. Okay? All right. And sorry, let me skip that side. So let me describe some calculations that I did with Bernardo Villarreal and Simon Gritschacher. When we started doing this, so the only calculations were those in Alejandro and Jose Manuel's paper. So there was a distinct lack of examples. I mean, for rational cohomology, they had basically done the entire calculation, but although I often have a hard time interesting non-algebraic topologists in this, I wanted to know what the integral cohomology was. I think sort of only algebraic topologists tend to care about torsion, or for the most part that's true. But we wanted to know what it was. So Ecom-G has a homotopy type of a finite CW complex. Which finite CW complexes do you get this way? Are they interesting? And but this is so. Going beyond the rational cohomology turned out to be pretty hard, and so basically what we have are a few low-dimensional examples. Okay, so what we did was calculations for the groups SU2, U2, O2, and SO3, but for SO3 we really only had the variant of the connected component of the trivial homomorphism. But for the others we took the whole group, Even in the case of O2, which is, O2 is not even connected, so it's definitely not covered by the results of Alejandro and Jose Manuel. And so for each of these cases, we calculated the integral cohomology ring. We calculated, so all of those, they only have 2 torsion. So we also calculated the mod 2 cohomology rings, and we calculated the action of the Steenrod algebra on the cohomology. And we also calculated and this is the most interesting part, the homotopy type of E, G. And they all had simple, but I found surprising descriptions. All right, so first let me show you the cohomology calculations, just so you see that they're kind of messy. Let me remind you that the mod 2 cohomology of BO2, that's very nice. It's just generated by the Stiefel-Whitney classes, W1 and W2. The integral cohomology of BON is also known, and it's much more complicated. This was computed by Brown, and I really liked how that paper starts. So his introduction is the following sentence. The other day I wanted to know what the integral cohomology of BON was. That's it. That's the introduction and motivation. I wish we could still write papers like that. So he wanted to know, and he computed it, wrote a paper. This is what you get for BO2. Those capital W's are the Bachsteins of the Stiefel-Whitney classes, and there's also the first Pontryagin class. Okay, so that's just to remind you what these cohomology rings would look like in the full classifying space. In the classifying space for commutativity, you get some extra classes, you get some extra relations. So looking precisely at what they are is not going to be interesting. I just wanted to show you that they're significantly messier than the classical ones. All right. So this is, now this result I feel is sort of at least nicer to state. We computed the homotopy type of E, O2, and it turns out to be homotopy equivalent to a wedge of S3 and 2 copies of S2. And now that you know that it's a wedge of spheres, you can use the Hilton-Milner theorem to compute as many homotopy groups as you want, at least as far as the tables of homotopy groups of spheres go. And as you can see, these get complicated very quickly. Look, pi 10 has a summand of z to the 308. And so these elements of homotopy groups, what are these? So these are homotopy classes of maps from Sn to this classifying space for commutativity. So they are transitionally commutative rank 2 real vector bundles on spheres, right? And the homotopy groups of just ecom, which is most of the I only have the table here for bcom, but the table for ecom only has some of these exponents slightly smaller. It's very similar. So the homotopy groups of ecom O2, what are those specifically? Well, that's the homotopy fiber of the inclusion from bcom O2 into BO2. So homotopy groups of ecom O2 are transitionally commutative. They are transitionally commutative rank 2 vector bundles. Homotopy groups of ecom O2 are transitionally commutative structures on the trivial rank 2 vector bundle over a sphere. Okay, so the homotopy groups of ecom O2 are enormous. They're almost as big as these. And all of those are just different non-isomorphic commutative structures on the trivial bundle. So the theory gets complicated. And for bcom SU2, well, we also computed the integral homology and the F2 cohomology, but as with the other group, the calculation I really like is the homotopy type of ecom SU2, which, I don't know, turns out to be surprisingly simple. It's homotopy equivalent to S4 wedge, the 4th suspension of RP2. And again, this means that you can compute its homotopy groups as far as tables of homotopy groups for spheres and suspensions of RP2 go. And so these are definitely not as crazy as the ones for SO2, just because it has one fewer wedge summand. But they're also sort of surprising and interesting. And computing this homotopy type was a completely ad hoc computation. There's no general method. We got lucky a bunch of times. There were several small miracles. And we just don't know a good way to compute these homotopy types in general. And to end, let me just mention that Alejandro and Jose Manuel already proved that. So we have this bundle there's this principal G bundle over B, O2, where the total space is this E, O2. And so this is a homotopy fiber sequence. And this means that you can think of this space as some kind of twisted product of these two up to homotopy. They prove that if you take loop spaces, it's actually untwisted, right? The loop space of B, G is just homotopy equivalent to the product of those two loop spaces. And Simon Gridschacher, in his PhD thesis, among many other things, proved that for a compact connected Lie group, it's not true without the loops. And our calculations give a new proof of that fact for SU2, and they give a pretty interesting example of spaces. These two spaces, B, SU2 and E, SU2 cross BSU2, they have isomorphic integral cohomology rings, they have isomorphic mod 2 cohomology rings, they have the same homotopy groups. In fact, they have homotopy equivalent loop spaces, but they are not homotopy equivalent, and you can see that because they have different actions of the Steenrod algebra. All right, thank you.
One very quick question. Well, thank you.
Thanks.